let's talk more about collisions. This is the first of, actually there's going to be quite a few different parts to this because we have to talk about lots of collisions. First though, we're just going to review what we already know about collisions. We talked about this last year in your first year of physics. There are two kinds, okay, two kinds of collisions. There's something called an elastic collision. Elastic. Okay. In an elastic collision, the total kinetic energy of a system is not going to change. Okay, that means, let's say we've got two, let's see, well, I should write this. Basically, energy is conserved is what we mean. Energy is conserved. So let's say we had two objects, okay, two projectiles. Let's call them mass 1 and mass 2 for just cuz, why not? And they are headed for each other. Oh, that should be straight. Hang on. I could do better than that. Okay, that's not much better. Oh, no. Come on. Wakey. Okay, I'm going to call this initial velocity of number 2. Yep. And then this one's going to be slower, and we're going to call that initial velocity of number 1. Okay, so let's say they're heading toward each other, and their energy is conserved, their kinetic energy is conserved. So when they hit each other, the energy might be rearranged somehow, but I'm going to have the same total amounts, okay? So E is not going to change, it's going to be constant. So right now, if you look at this, what we have for total energy is the kinetic energy of number 1, initial kinetic energy number 1, plus the initial kinetic energy of number 2. So what I have here is, 1/2 m1 v01 squared plus 1/2 m2 v02 squared. Okay. Whatever this number is, you know what? Just to make this easy, 32. It's 32 joules. Boom. Okay, whatever. This is an example. Okay. That 32 is not going to change. Okay? So when these things collide, boom, that collision happens. Collision. I don't know why I had caps and then I made a lowercase. Let's make it uppercase. That was weird. Okay. Whatever these things are doing, and probably they bounced off each other somehow. Okay? In fact, most elastic collisions are going to look just like a pool game, where the balls just bounce right off of each other. It might not be the same velocity. Oops, why did I do that? Wow. It's Sunday night, and I am waiting for Downton Abbey to come on. And then I'm going to go to bed, because that's what I do with my life. Okay. Alright, this is going to be my final velocity of number 1 and my final velocity of number 2. Okay. Whatever they do, and however it ends up in the end, they had better still have 32 joules between them, because that is physics, and physics is king of the universe. Okay? So the total energy must still be 32 joules. Okay? Turns out the momentum is also conserved. Should I throw that in there too? Momentum is conserved. Total momentum is conserved. Okay? So if their momentum was well, this one's positive and that one's negative. I'm gonna say the total momentum was negative 5. Okay, then boy, their total momentum had to better still be negative 5. Okay, they have to be. Now, in real life, you don't get a lot of these, because most of the time you lose some of this 32 joules, this energy, to other forms of energy. It's not going to stay as kinetic. Maybe when the balls hit, they get deformed a little bit, and as they're being smushed, they heat up a little bit, In that case, some of that 32 joules will go to thermal energy. Okay, maybe when they hit, they make a good old smacky sound, you know, crack. And when that happens, some sort of energy's got to go to make the sound. I mean, sound doesn't come from nowhere. It's a wave, and wave is just an energy just traveling through the air. So some of that 32 joules will go to sound. So again, in real life, you don't get many of these elastic collisions. You get some collisions that are very, very close, but they're not perfect. What you do get a lot of is inelastic. Inelastic. And you gotta enunciate really carefully because you're saying like an elastic and inelastic. So put an when you're doing, you know, you're talking. It was an elastic collision. Sounds a lot like it was inelastic collision, so be careful. This was an inelastic collision. You can't see me, but I'm totally overdoing my mouth movements here. It's crazy. Anyway, in these, total momentum is still conserved, which is good. Come on, conserved. But energy is not. Okay? In fact, what you'll mostly see with inelastic collisions is when these two things hit, they don't stay two things. They smack together and make one big blob of a thing. Okay? So most of the time, with inelastic collisions, what you will have, same setup, by the way. No! Why can't I draw a straight line with light blue? I love that color. It just doesn't like me. Okay. Like tacos. Alrighty. When they hit, let's say they start off with the same stuff. So my total energy was 32 joules. My total my total momentum was -5 Newton seconds. Okay. Then the collision happens. Collision. Let's see if I can. Yeah. Collision. Get the eyes right this time. Collision happens. In the end, we don't have mass 1 and mass 2 anymore. What we have is a blob that is all smushed up together with the other blob. So basically I have a big blobby blob here. Looks like the blue is eating the dark blue. Squish. Okay. Where that whole thing now has a total mass. It's m1 plus m2. And the whole thing is moving as a blob together. Now, I know that the total momentum is still -5 Newton seconds. That can't change because momentum is conserved as long as there are no outside forces. So, that means that the only thing, well, there's only one thing here. So that must be using all of that -5 Newton seconds. So this thing's moving to the left at this point. With some final velocity v. Now I'm just going to call it v, not v1 or v2, because it's not the velocity of 1 or 2, it's the velocity of just the one thing that's left, this blob. That really looks like something, it's like an amoeba eating something else. Wow, kind of freaking me out a little bit. Anyway, we will be dealing mostly with inelastic collisions. Okay, in fact, I don't think I've ever seen any kind of quantitative analysis of elastic collisions on the AP test. They do sometimes ask about it. They'll ask like, is this an elastic or inelastic collision? Why? And you talk about how energy was conserved or not conserved. But I think the only math I ever see is on inelastic, and they do love those. Those happen all the time. In fact, I've got several problems waiting for you guys. And we've had several problems that with earlier in the year where I kind of cut out the inelastic collision part because we weren't ready for it. But anyways, we'll do several of these in 1 and 2 dimensions, but that is for another lecture. I'm stopping now.